afternoon. As you can see by the title, the application of my study is pretty far from those we are listening in these days, so I hope I can introduce it to you as clearly as possible. Okay. So, we are dealing with a pathology that affects the artery in our legs, that is a peripheral artery disease. You can see with this pathology we are dealing with an invasive disease that prevents the correct blood flow in the artery. So the clinical gold standard is stenting, so that means the insertion of a metallic grid inside the artery to sustain it. However, due to gait, these arteries that passes behind our knees are subjected to a complex state of loads that are compression, pinching, bending, torsions. And if we consider that we can make an estimate of about average 1 million gait per year, stents are subjected to fatigue failure. And you can imagine if a stent fracture inside our body, that can be a really severe consequence. These stents are made of nickel titanium alloys, which belongs to the shape memory alloys. These are temperature-dependent materials, and as you can see from this plot, they are characterized by strongly non-linear mechanical behavior, and in particular, they can cover elastic deformation up to 7–8%. And that is pretty useful in lifetime of a stent, because stents need first to be trimmed, so their diameter needs to be reduced to fit on the catheter in order to be inserted inside the body. Then, when they arrive at the location, they need to be expanded, and at this point they cannot expand freely because they encounter the artery, and only at this point the real cyclic loads due to gait starts. So the standard approach for the design and verification of this device require in vitro testing. In particular, the regulation requires testing long experimental campaign up to mimicking about 10 years of equivalent working cycle. And as you can see from these experiments, we can only obtain the information about a failure or not failure. For this reason, in the last year, these in vitro studies have been coupled with a numerical simulation that can give more information regarding the local state of stress and strain, but also investigate different boundary conditions at the only computational cost. This kind of combined approach was the object of my previous research, in which I used a finite element model of a stent. I simulated different boundary conditions, I extracted stresses and strain, and through proper fatigue criteria, I tried to investigate which was the most critical zone of the stent. Then I performed those experimental campaigns in order to validate my results. That is a macroscopic approach. To go further, to complete this study, we wanted also to go through another way. That was a more local one. I mean, we observed that on the stent surface are present defects in the order of microns. And if we are going at the fracture location, this is a fracture of a stent, we can see that sometimes these defects act cracking is initiated. For this reason, we decided to investigate if a fracture mechanics approach could justify or interpret this failure in the stents. So I started from simplified geometry, so you can see I'm not studying the stent, but a stent-like specimen. This is a multi-wire specimen that is laser cut from the same source tube of the stent and underwent the same thermomechanical properties to guarantee the same materials. Moreover, these wires have the same dimension of the stent struts, but their simple geometry allow an easier stress-strain evaluation. I performed a fatigue test on this sample, mimicking body temperature at 37 degrees, and all these samples were tested in order to mimic the stent life story. So they were preloaded to mimic the crimping, partially unloaded, and then the effective fatigue cycle, investigating different combination of mean and altitude strain, was performed. I also performed finite element analysis in order to have more detail on the local stress and strain path. This is the conventional representation of our results in a strain life diagram. As you can see, there is not much correlation. But moreover, what we could find that there were different deformation regimes according to the different mean and amplitude strain. In particular, those results in blanks, you can see in the cycle, were characterized by a pseudoelastic behavior, so with high hysteresis during their cycling. There were others in blue which were experiencing almost elastic response, and another case that was the one in red, which had a mixed behavior. For this reason, we decided that probably using an energetic criterion could be a good choice in order to take into account these different dissipation regimes. What we did is start from the computation of the cyclic J integral, so from an elastic plastic fracture mechanics approach. I'm using this simplified formulation from the work of Patriarca. In this formulation, the cyclic J integral is function of the shape and size of the defect, and also on the elastic and plastic contribution of the energy. And starting from this, we went through each condition. We considered the stabilized cycle, and fitting by Rambeck-Osgood, we were able to find out first the n prime, and then all the other parameters needed for the computation. And we repeated that for all our cases. After that, moving on the defects, we did some imaging observation, and we were also able to make the hypothesis that these defects were semicircular on the surface. From our measurement, we were able to identify different crack lengths from 2 microns to 20 microns as the initial defect size. While as for the final dimension that is needed for fatigue prediction, always from observation we set 150 microns, that would be a reasonable measure, but also this value is not influencing a lot the prediction. So, as a first proof of concept, we are with the strain life diagram, we made the hypothesis of a crack of 2 microns, and just plotting the initial value of the cyclic J integral against the fatigue life, you can see we obtain a much better correlation. But we are not happy about this. We wanted to perform an effective fatigue prediction of these results. And so we needed the fracture properties of this material. We were lucky, we went through the literature, and in these studies of Stankiewicz and colleagues, we found these experiments involving samples that were obtained through tubes that were really similar to those used in stent production, and that is important. So we focused on the R ratio of 0.7, that is a condition close to that of the stents, and we converted the information in stress intensity range into the cyclic J integral, making some hypotheses, just considering plane stress, the elastic contribution of the J integral, and since we needed the value of the elastic modulus of the material, and in this work it wasn't available, we selected 2 cases, 50 gigapascal and 62, that are reasonable value for this material. And we were able to identify the C' and N' parameters for crack propagation. Then, with an iterative approach, we were able to simulate the predicted number of cycles. And as you can see, I'm showing the results with an initial crack size of 8 microns, that is an average value among ours. And we were pretty satisfied with these results, even if we have to say that choosing different initial crack length can affect the prediction. However, we wanted to apply this on a more complex case, which is the one of the stents. So I performed 2 years ago this in vitro campaign on stents that were testing under multi-axial loads, and I also performed numerical simulation. In particular, I had these stents that at a specific load case, I tested 3 devices, and all of them broke at about 20,000 cycles, and all of them broke at the same location, as you can see. So, from the observation, we could make the hypothesis of an initial crack length of 2 microns and a final crack length of 50 microns. And then, by applying the same procedure, so I used the numerical model in order to go at that location where I had the failure. I was able to check the hypothesis of mode 1 propagation, and from here I extracted the value of the maximum principal stress strain at the stabilized cycle. At this point, I performed my prediction. You can see many lines because I'm plotting the results of all the elements of this critical area. And according to the two elastic modules that, as before, as an influence in the prediction, we could say that we are also in this case we were satisfied by these results. So we know that this is a preliminary study, but you have to know that damage tolerant approach has not been widely used in the fatigue assessment of cardiovascular devices. So this is our first attempt, but our results show that the use of the cyclic J integral gives promising results. We know that we have to work more to verify these on more devices, more loading conditions, but for now that's it. Thank you very much.
Thank you for the presentation. One or two questions?
Could you comment on, you said that you chose the R0.7 because it's more related to the application, so to the...
I couldn't hear, sorry.
You said that you chose the ratio of R0.7 because it was more similar to the application. How did you came to that conclusion?
I mean, thank you for the question. I mean, in the literature, we could find a lot of results with R equal to 0 or almost 0, but from that is also the numerical model that is helping us. I mean, for the multi-wire specimen, that is quite easy to understand which is the ratio because we have all the gauge length is behaving the same way. So obviously that in a stent is an assumption, but from the we have to decide if we consider the macroscopic R ratio from the applied load, but we know that in a stent where the complex load is really makes a different story at the local level, we need to evaluate what is going. So this is an assumption based on this case, so what's happening at the local scale of these stents. Obviously, that is a point. This is a really good question. But I can exclude that in this critical area, the ratio will be low. So it's more likely to have a higher ratio. Thank you.
Other question, please?
Just curiosity. The effect of young modules. Did you consider the variation of young modules with the fraction of mark inside the transformation? Because I see that you did simulation for different values of the young modules.
That value of the young modulus, the two different ones were used to convert the data from the literature. But then in the computation of the cyclic J integral, we use the effective young modulus, so taking into account the different slopes due to the material complexity. Thank you.
Okay, so thank you very much.